Assalamu alaikum. Let's start with the next thing, and that today is chemical formula, nomenclature. Now that is a term that many students might find difficult to just relate to. Like, nomenclature sounds such a difficult word, and of course it may be intimidating. But today our goal is to make sure that by the end of it, this lessons you are very familiar with it and masters of nomenclature and formula. Now, what exactly is nomenclature? Nomenclature simply means, so this word, it simply means that you have a naming scheme. Scientists, they have a naming scheme, a system for how they name different chemicals. Now, today I'm not going to talk about naming scheme or nomenclature of organic substances. We'll deal with that later on. But for now, I'm just going to go over the inorganic, the covalent, the ionic compounds, and how we name them. Of course, there are a couple of things that we need to memorize for them. So I'll tell you about those as well. So, all right, let's begin. The first one, whenever you take any compound, the first thing you have to know is what kind of bonding would this have? Because if you know the difference in their bonding, it really makes it easy to name it. And that is one reason chemical names are so much better than other ordinary names. I'll give an example. When I say water, now anybody who is unfamiliar with the concept of water has absolutely no idea which substance I'm talking about. Imagine you did not know what water was, right? Or if water is really familiar, maybe think about acetic acid. Like, if you do not know what acetic acid is, apart from this word acid, there's absolutely nothing else that I've told you, right? But if you knew the chemical formula for this and the chemical name for this, you will know so much more about this compound just by looking at it. For example, when I say water, then I am not telling you anything about the substance, what is it made of, what goes into it, what kind of properties it has. All I'm saying is water. But when I say H2O, then I am giving you so much more information. I'm telling you it has two elements in it, hydrogen and oxygen. I'm telling you that the ratio in which they're related to each other is 2:1. And I'm also telling you, if you have some knowledge of chemistry, then you know that because it's hydrogen and oxygen, they are going to have covalent bonding. Not just that, if I try to take its chemical name, I will convey all of that information to you right away. For example, when I say acetic acid, then most people who are unfamiliar with chemical formulas or chemical names will only infer from this that it's an acid. But when I say, oh, this is CH3COOH, then everybody knows that first of all, it has three different elements in it. And this is the way they're arranged to each other. Maybe these three hydrogens are joined to one carbon, and maybe those oxygen are joined to that carbon, and then there's another hydrogen. So the formula and the name, the chemical name of this thing is ethanoic acid, conveys a lot more information than the common name that we have. All right. So naming scheme or the nomenclature is there to tell us what the chemical formula is and how we can name that thing based on whatever that substance is. All right. So that's the primary goal today. All right. So here's what we do. We start by taking out things that are covalent. Okay. So covalent substances, how do we name them? So first of all, because they're covalent, that implies that they most likely have just non-metals in them. Now, again, in O-levels and IGCSE, there's only one exception to that, which is aluminium dichloride, AlCl3. So here's the thing. In covalent substances, when we are going to name them, of course, we are going to name their molecule or their lattice. Those are only two options, right? Either you get a molecule or you get the lattice. Now, when it comes to the molecule, then you tell the molecular formula. So molecule can have molecular formula. It can have empirical formula. And again, it can have a structural formula. Now, there are other kinds of formulas as well, but for now, we'll just stick with these. So here's the thing. When I say glucose, then I'm not saying much about it. I'm just saying glucose, that's a name. But glucose has 6 carbons in it. So I'll say C6H12O6. Now this is my molecular formula. It is telling me exact number of carbon atoms, hydrogen atoms, oxygen atoms that are present in one glucose molecule. Now, if I take a ratio of these, then I know that all of these numbers are divisible by 6. So when I divide it by 6, I get C1H2O1. This is my exact number, okay? Exact number of these particles. And this is my ratio of these particles. The simplest ratio, in fact. It's not just any ratio, it's the simplest ratio. The simplest ratio is basically my empirical formula, and my exact number is my molecular formula. Now, its structural formula is beyond the scope of O levels in IGCSE because this is a very complicated kind of molecule, so I don't want to go into that. But the point is that I'm able to know exactly what this has, the number, what ratio they're in using empirical formula, and if I want to know the structure, I can know it from there. So whenever you take a molecule, you look at the molecular formula, the empirical formula, the structural formula. If the thing does not have a molecule, if it is a giant structure, then we always go for the empirical formula, because empirical formula gives me the ratio, okay? So for example, when we have silicon dioxide is a giant structure very similar to that of diamond. So you have silicon, which is attached to 4 oxygen, and every one of those oxygen is further attached to silicon, and it keeps on growing like that, okay? And it keeps on growing like that, and it's a tetrahedral structure because these 4, this is basically my unit. Now this thing, what's the ratio? Every silicon and every oxygen is there, and you can technically not really count how many silicon and oxygen are there. Sure, we have ways of measuring exact number, but for now we have countless number of silicon and oxygen. What I do know is that for every silicon there are double the oxygen. Why? Because every oxygen is attached to 2 silicon, and every silicon is attached to 4 oxygen. So there are twice the number of oxygen than there is silicon. So my formula is going to be SiO2, and that's my ratio. That is silicon dioxide. Now that's the primary difference, that if something is molecular, we can have different kinds of formulas: molecular formula, structural formula, empirical formula. But if something is giant, we just go for empirical formula. In fact, anything that has a lattice, we always go for the empirical formula. That's a covalent substance. All right. How do we name them? Now the naming scheme is pretty straightforward for covalent. You count how many atoms you have, and that gives us a prefix. You know what prefixes are? So for example, my name is Ahmed, but sometimes when I'm called for different things, some people call me Mr. Ahmed. All right. If I go on and do a PhD someday maybe, then I will be Dr. Ahmed. Now that Mr. and Doctor, that's just a title, right? And it's telling something about me. For example, in this case, it's telling my preferred gender. If I was a doctor, it would tell my qualification probably. So it does tell something about me. So a prefix is just another thing that we add before the name that tells us something about that substance. So we count different things. So for example, if you have 1, 2, 3, 4, then we have these prefixes. 1 is mono, 2 is di, 3 is tri, 4 is tetra, and from 5 onwards we use the, I think it's Greek, that penta, hexa, hepta, octa, nona, just the way we have for months of the year or polygons in geometry. So it's just like that. Now we usually don't use mono unless there's a confusion. If there is same substance making different things, same elements making different substances, then we use mono. Otherwise we try not to use that. So what do we do? So I'll take an example. We just had silicon dioxide. Why am I calling it silicon dioxide? SiO2. So what's the ratio? This is 1 silicon, so I don't really need to mention it for the first one. So I have silicon here, and I have oxygen here, so that's oxygen. But because it's the last one in the name, I put IDE next to it. So that is basically telling me that the name is finished. This is the last thing. And how many oxygen do I have? I have 2 of them, so I'll say dioxide. So the di word is there to tell me that I have 2 oxygen. Okay, so basically using this, I'm able to name this. So let's take another one, C2H4. Now, how would I name this? Now, of course, this is an organic compound, and for organic compounds, we have different techniques. But using this, what would I say? I have 2 carbons, so I'll say dicarbon, 4 hydrogen, so tetra because 4, hydrogen because hyd, and then this is the last one, so tetrahydride. Okay, pretty straightforward, right? Of course, when you study organic chemistry, your friends might name it differently, but we'll get to that, nothing to worry. All right, let's take another one. What if we have 3 things? For example, C2, H2, Cl2. All right, so all of them are 2. So I will say I have dicarbon because 2 carbons. But now hydrogen is not the last one. So I wouldn't really say hydride. I can if I want to, and that won't be wrong. But I can say instead of saying hydride, I can say hydro. And that just basically makes a continuity. So it's fine if you call it dihydride or dihydro. And then I have 2 chlorine, so dichlor. And then because I'm adding it, this is the last one, dichloride. There you go. So dicarbon, dihydro, dichloride. Again, we have better mechanisms for organic substances, but this must do. Now, when do we use mono? We don't prefer mono all the time, but let's suppose I have carbon and I have oxygen and they're both joined together. Now, when carbon joins with oxygen, it either makes carbon monoxide or it makes this one. Now, these are 2 compounds, both of them made from oxygen. So I can't really say carbon oxide because, wait a minute, how many oxygen are we talking about? 1 or 2? So for that confusion, to avoid that, we say this is carbon with 1 oxygen. So that's carbon monoxide. Notice that I did not write O for mono and O for oxide. I just combined them. So carbon monoxide, silent killer, which we usually call, and carbon di because there's 2 oxygen, so dioxide. So that's the name. That's how you name these things. Now, despite all of that, there are a few compounds with some common names or names that are archaic, and we don't really need to get into how they got that name. So there are a few in O-levels and IGCSE that you should be familiar with. Of course, the first one is water. Now that is something everybody knows, is H2O. Then we have ammonia. Again, this is a name that's not telling me about its structure, its composition, but it's a name that has stuck for many different reasons. So this is ammonia. Similarly, methane or methane, CH4. Again, there's a reason why it's called methane, but we don't need to get into that at the moment. Then we have hydrogen peroxide. Again, I don't need to tell you that there's a reason why there is a per in there. But again, we don't need to get into that. So hydrogen peroxide, that's another thing that you need to know the name of. All right, so we have common names for the things. We have things that have the names like mono, di, tri, tetra with the element in there, and then ide for the last one. And then we have common names for these 4 things that we should know about. Now, there is another class of compounds which we call acids. Now, the acids are covalently bonded. But here's an interesting thing. Acids are, despite being covalently bonded, they can conduct electricity, they make ions, and that makes them very interesting. Okay, so for them, we have a very easy mechanism. Every acid has either, it has to have hydrogen, right? It gives hydrogen. Things can be acidic if they don't have hydrogen, but any acid itself must have hydrogen. So I'll take a few examples. I have HCl, HI, HBr. These are acids from group 7. Now the thing is that all of them have just 2 elements in them, hydrogen and chlorine. So for this reason, we'll call this one hydrochloric. Hydro because hydrogen and chloric because chlor. And then because it's acid, to say that, we're going to say IC at the end. So acids, their names end in IC. So I will say that their family name is ic. All right, so acids end in ic. So HI, this one, will end in hydro for hydrogen, and iodine, so IO, and then IC, so hydroiodic. Similarly, this one is hydro because hydrogen, and bromine, so that's bromo, and then ic for the acid part, so hydrobromic. All right, so that is if you have 2 different elements to an acid. You just name the hydrogen part, that element, and then put IC at the end of the name. Now, what if you don't have two things? What if you have multiple things? For example, HNO3 or H2SO4. Then in this case, how do we name them? Or in fact, H2CO3 or H3PO4. These are some of those that we use in our syllabus a lot. So here's the thing. You do not name the hydrogen in there. You do not name the oxygen in there. So that's the preferred method that we have. We do not name the hydrogen or oxygen. So skip. Sorry, what happened here? Yep. So skip hydrogen and oxygen. So skip that. All right. So what should I name them? So the middle one with IC. You see, it's really simple. So you skip hydrogen, you skip oxygen if you have more than two elements in there, and just name the middle one. So the middle one in this case is nitrogen. So this is going to be nitrogen with ic at the end. So nitric acid. There you go. It's pretty straightforward. This one, name the middle one sulfuric. That is sulfur, right? So sulfuric or sulfuric, which we call it. Similarly, this one is carbon. So carbonic or carbonic, whatever you want to call it. And then this is phosphorus. So it's going to be phosphoric. See, so all of them have IC at the end of the name to signify that they're acids. And we are not naming the hydrogen, we're not naming the oxygen. We just know that that is the way they are. All right. So, for example, I'm going to give you this acid. Try to name this acid using this technique. Okay, so that is when you name acids. Now we have covalent substances. If we have molecular formula for the molecule, of course we use mono, di, tetra and all that. For lattices we do the same thing, but we just use the empirical formula. We just give the simplest ratio. For acids we see if we have two of them or if we have three of them. Now that's all fine. Is there any metallic compound that is covalent? Yes, there is one in your syllabus, that is AlCl3. And because it's covalent, we will use mono, di, tri, tetra in this. So I have aluminum here. So aluminum. And there is 3 chlorine. So I'll say trichloride. So aluminum trichloride, that's the name, and that tells me that it is a covalent substance. Just using that tri, I know it's right away a covalent substance, even though it is metal, which means that now I can infer it will have a low melting point, low boiling point, low density, it will not conduct electricity. All of those things are coming from my knowledge of covalent bonding, which we studied in the last class, and you can go to that link and see that class if you need more information on this. All right, excuse me. All right, so now let's try move on to ionic substances. How do you name ionic substances? Now the thing with ionic substances is that they always have a lattice. There's always some large network of positive ions surrounding by negative ions, and that is why we will always use their empirical formula. Again, that is something that many students do not know, and you should, because we always take that ratio. All right, so ionic substances, when we have them, we take their ratio. Now, how do you name them? The names are again very simple. You name, because ionic substances, are made from cations and anions, we say the name of the cation and then we say the name of the anion, and usually at the end we put either IDE or something. So we just name the cation, we just name the anion. So how do you name the cation? Cation, for example, sodium with a positive charge is called sodium ion. There's no different name. Sodium ion, that's what it's called. Calcium with a positive 2 charge is called calcium ion. And aluminum with a positive 3 charge. It's called aluminum ion. Now, what is common in all of them? They are all not transition metals. Okay, that is something that is common in all of them, and that is something we should be aware of. What if we have transition metal? Then I will say iron, for example, has one ion with +2 and one ion is +3, and that is the reason that transition metals hold a special place. Transition metal ions can have multiple different charges depending on what ion you have. Which is why whenever we name them, we need to mention which charge we are talking about. So this one is iron 2 and that one is iron 3. Notice that I'm using Roman numbers in parentheses, and that's the way it should be written. So this is iron 3 ion and that is iron 2 ion. So judging by this, can you think of the name for this charge or this one or this one and this one? Take a minute. Now here's the thing. This one is copper with a positive 2 charge. So we say copper 2. That is chromium with a positive 3 charge. So we say chromium 3. And all that is fine because they are all transition metals. But here's the thing. Not all of these are transition metals. Sure, Sharmeen, just give me a minute. I'll explain what that is. Zinc and silver, while they are present in the transition metal block, we do not regard them as transition metals in O levels and IGCSE. There are reasons for it. Again, there is a reason for everything we do in chemistry, and I know it can sound sometimes very frustrating, but we have to keep things simple for you. That is why we are just going to tell you that this one is not considered transition metal at this stage. So this one will be zinc. That's it. It's not zinc 2, and this one will be silver, not silver 1. Okay, now even though you find them in the transition metal block, does not mean they're transition metal. In fact, there is another one, a newer one that hasn't been touched upon in past papers before, but you should be aware of it. That is this one. This is scandium, and this is again not transition metal, so it will always be +3. So there is 3 ions that are found in transition metals, but you need to remember the name of these, and I will highlight these ones. You need to memorize these charges. +1 for silver, +2 for zinc, and +3 for scandium. Okay, and those are the things that you need to know about. So these are the ones that you need to memorize. All right, so that's how you name the cation. It's pretty straightforward. What about anion? An anion you can name again through a similar method. What you do is you take the charge and you just see that if it is negative, you end the name in "ite." So I'll give you some of them. For example, chlorine with a negative charge will be chloride. There you go. It's a chloride ion. Similarly, if you had bromine with a negative charge, or iodine with a negative charge, or sulfur with a -2 charge, or nitrogen with a -3 charge, or very rarely carbon with a -4 charge, then what do we call them? This one is bromide, iodide, sulfide, nitrite, and carbide. Of course, these names come from them knowing that these are negative ions. Now, how do I know the charge? Look it up in the periodic table. The total group number plus the number should be 8. So group number 7 plus 1 is 8, right? So the charge is -1 for group 7. For sulfur, group number is 6, -2, that is 8, right? So sulfur has 6 electrons. I give it 2 more, that's 8 electrons in the last shell. So 6 plus 2, that's 8. So the charge is -2. Nitrogen group 5, 5 plus 3 is 8, so -3. Carbon is group 4, 4 plus 4 is group 8, so -4. Remember, all non-metals prefer the negative charge side, and metals prefer the positive charge side. We say that metals are oxidized and non-metals are reduced. Again, this is strictly for O levels and IGCSE syllabus. All right, moving on. So we have these ones, and these are the negative charges for all of them. And you can simply name them based on this. So for example, think of the name of this thing with a -3 charge. Now, how do I know it's -3? Because it's in group 5. 5 plus 3 is 8. And -3, it's a non-metal. Now tell me, what will its name be? This is phosphorus. So phosphide. And there you go. That's how you name the positive ion, the negative ion. So for example, if I were to react sodium with chlorine, I'll call it sodium for sodium ion and chloride for the negative chlorine ion. So that is sodium chloride. If I react aluminum with bromine, I'll call it aluminum bromide. If I react iron 3 with nitrogen, I'll call it iron 3 nitrite. So if you're able to name the cation, if you're able to name the anion, just put the names together and you have your Ionic Substances name. So you see, nomenclature is very, very easy. You just need to know the name of the elements that you have and what ions they're making, what charges they have, and you're good to go. For transition metals, you need to remember the formulas, the charges that you can get. So these are the 4 that are in your syllabus. You need to know the charges on these things. All right. So for example, if I told you that there is this compound that is joining V plus 5 and O negative 2. Now, what will the name be? Just look at the ions. This one is vanadium, which is a transition metal. So I must say vanadium 5 because vanadium with a plus 5 charge. And then oxygen is forming a -1. How do I know it's a -2? Look it up in the periodic table, group 6. So group 6, 6 plus 2 is 8. So -2 is the charge. So oxide, vanadium 5 oxide, that's the name of this compound. All right, so it's pretty straightforward how you name this. All right, now let's move on. How do you write the formula of this thing? So it's pretty straightforward. I'm going to share a worksheet with you for all these formulas, that how do you write the formula and how do you know the name. So make sure that you practice from that worksheet and I will share the solution with you. All right, so let's write down the formulas. Now, when you write formulas, I have my own method of, I call it ratio flip method. Okay, again, this is just a name that I've invented. So ratio flip method, it's a pretty straightforward method. What you do is take the positive ion, take the negative ion. So let's take that example we just talked about, V plus 5 and O negative 2. Now I want to know its formula. So here's what I do. The charge on vanadium is 5, the charge on oxygen is 2. I'm not concerned with the negative or positive thing. I'm just concerned with the number. The ratio is 5 to 2. Flip it. And that makes it 2 and 5, right? So V2O5. Just make sure you write it downwards, because this is telling me that I need 2 vanadium and 5 oxygen. Now there is a reason why that is the case. What's happening here? Let's try to make sense of that. Vanadium is losing 5 electrons. Oxygen is gaining 2 electrons. Now, how many oxygen will neutralize this vanadium? So let's see, one is losing 5, one is gaining 2. What's their LCM? The LCM is 10, right? 2 and 5, their LCM is, I'm using the ladder method for LCM. You can use any other method. So 2 and 5, that my LCM is 10. That means I need both of them to involve 10 electrons. Okay, just give me a minute, my laptop is dying. Let me put it on charge. Yeah, so their LCM is 10, which means I need both of them to give or lose 10 electrons. So how many vanadium do I need to lose 10 electrons? 5, right? One is losing 5, so 2 will lose 10 electrons. That is why I need 2 vanadium. And how many oxygen do I need to gain 10 electrons? When one of them is gaining 2, I will need 5, because 2 times 5 is 10. And all of that math, you can avoid it. You can do it right away by just doing the ratio flip method. What if I don't have a different number? What if I have aluminum, which is Al plus 3, joining nitrogen ion, which is nitride ion, with a negative 3? Now here's the thing. How many ions of nitrogen do I need to take 3 electrons? 1. How many aluminum ions do I need to give 3 electrons? 1. So the ratio is 1 to 1. Look at the numbers. 3 ratio 3. What's the ratio? 1 ratio 1, right? So I just take that ratio, 3 and 3 is 1 to 1, flip the ratio, and you have ALN. Alright, so that's it. ALN. That's it. That's the ratio flip method. It's pretty straightforward and you can use it for many different combinations. So let's take another example. Let's say I have iron with plus 2 charge and carbon with negative 4 charge. In this case, I just need to do the ratio flip method. And what's the ratio? The ratio is 1 and 2. Why? Because carbon has a 4, iron has a 2. 2 and 4 are in the ratio 1, 2. Flip it and you get 2, 1. So my formula is Fe2C1 and that's it. That is my iron 2 carbide ionic compound. That's the formula of this thing. Alright, so for whatever ions you have, you take the ratio flip method and it works. Now the last thing for today, which is molecular ions. Molecular ions are basically ions that are made by covalent bonding. Just like I told you that metals form covalent bonding as well, there are non-metals that are forming ions. Okay, now molecular ions, again, many students, in fact, they do not know that molecular ions exist, and even if they do not know what kind of bonding they have. An examiner knows this as well, which is why examiner sometimes gives you a question in the exam that which of these has both ionic and covalent bond, and anybody who doesn't know this might be blank, which won't be the case if you study this thing. So here's the thing. Molecular ions are basically ions made by covalent bonding, which means once they form ion, they're going to do ionic. So any molecular ion, if it is present, the compound will have both covalent and ionic bond. So there are a few of them which we need to remember. So you must know this. So we have sulfur with a negative 2 charge over here and a 4 oxygen. This one, this one, this one, and yeah, these are the ones that we have. Now, what are their names? This one is sulfate. Notice that it doesn't have "ide" at the end. It's an 8 thing. That's a hint for us to know that this is molecular ion. This one is nitrate, carbonate, phosphate. So they're all pretty straightforward, following a trend. These 3 are slightly different. This one is sulfite. This is different from sulfate because it has lost 1 oxygen. It has 1 less oxygen than sulfate. This one is a positive ion. This one is going to be ammonium. It's made from ammonia and it has IUM at the end to signify that it's a positive ion. There's another molecular ion that has been tested, I think, just once in the exam, this one, which, because it's again made from, it's a positive molecular ion, we say it is hydronium. Okay, you will notice one thing. In all of them, oxygen has not been named because oxygen is a common thing in every one of them. So hydronium, phosphate, sulfite, carbonate, nitrate, sulfate. Hydrogen has not been named, but there's one in which oxygen has not been named, but there's one in which it will be named, which is hydroxide. So this one is hydroxide. Now these 8 molecular ions, you should know them, and remember that any substance that has these ions in it will have both ionic and covalent bond, except if it is made with hydrogen. All right, if it's an acid, otherwise, if it's an acid, then no. But if it's any other compound like sodium or anything, then this will be the case, that it will have both covalent and ionic thing. So just remember that metal plus molecular ion has both ionic and covalent bond. So what will we do if we have something like this and we want to make a formula? Pretty straightforward. Use the ratio flip thing. So for example, if I have copper plus 2 charge and sulfate with negative 2 charge, what is the formula? Just take the charges 2 and 2. The ratio is 1 to 1. Ratio flip. So flip it, that's 1 to 1, right? So CuSO4. And what will its name be? It will be copper 2 because copper 2 ion was present and copper is a transition metal. So copper 2 and sulfate, which is the molecular ion in this case. What kind of bonding it has? Both ionic and metallic, ionic and covalent. All right, what if I have different charges? For example, if I take this same substance like sulfate ion, but I react it with Fe3, which is iron 3 ion. Then the ratio, again, 3 and 2, flip it, you get 2 and 3. So here's how it goes. So 2 and 3, right? So Fe2, SO4, 3. But wait a minute, how do I know it's not 43? So I need a way to know that this is not 43. Also, 3 should go for the whole sulfate thing, not just oxygen. So for that reason, we put parentheses. So now it tells me that I have 2 iron, 3 ions, because the name is iron 3, and sulfate, and I have 3 of them, so 3 sulfate. And that's it. What's their LCM? 6, which means that 2 iron atoms lost 3 electrons each, and 3 sulfate ions gained 2 electrons each. And that is how they were able to make this compound, which we'll call iron 3. Don't be confused. Don't say it is iron 2 because the charge is what matters. Iron 3 sulfate. And there you go. So that is how you name these things. That's how you make formulas. And in any lattice, we use empirical formula. So only case where we use molecular formula is when we have molecules. I hope you understand it. I'm going to share a link for the worksheet. Make sure that you practice it, and I will share the solution of that in another video. I'll see you in the next class. Make sure that if you find this class interesting, ask your friends to join in, share, subscribe to the channel. Thank you so much. Allah Hafiz.